But I wanted to tell you a little bit, I do feel a little bit kind of closer to a bunch of engineers than I do to a bunch of business students. I think we have a little bit more in common. But I'm not an engineer myself. I'm a radio astronomer by training. I grew up in the UK, hence the weird accent. But I'm a scientist. I'm kind of an end user of the instrument. But I've got to know a lot about how we actually build these instruments, and I really want to kind of try and approach this from a bit of an engineering perspective today and tell you a little bit about how we're doing what I think is sort of one of the most kind of incredible but also sort of bonkers experiments that's taking place here on campus, and that is the Breakthrough Listen Initiative, and I'm going to tell you a little bit more about what that is later on in the talk. But first, I wanted to set the scene, and I wanted to take you back about 40 years and to show you an artist's impression of all of the planets that were known outside of the solar system at that time. And the situation has changed since 40 years ago. So there's some engineering actually that's been done that's enabled us to find planets outside the solar system. And here are artist's impressions of some of them, and an artist's impression of the Kepler spacecraft, which was responsible for many of these discoveries. So we now know of over 4,000 planets that are going around other stars outside our own solar system. When I was in high school, there were 9 planets. Poor old Pluto got demoted. I mean, that had nothing to do with me, but was that my laptop making that noise? Or?
Probably, yeah.
That's probably like, it sounds like a Slack notification, which is weird because I have notifications turned off. Maybe I can turn the volume down on here. Is this going to screw things up? Maybe I should just leave it and you can kind of deal with the occasional click in the background.
I'm wondering if we should get these lights down too. Can you guys see okay? Or should we get the lights down?
Some of the images are going to be a little dark, so we might want to turn them down a little bit, potentially. So, Pluto got demoted, but in exchange, we got thousands of confirmed planets. The reason why these are artist's impressions is because it's actually really difficult to take pictures of planets, and even the best pictures that we have, these planets are just single pixels on a detector, but we can measure the properties of them. We can essentially figure out what their masses are, we can figure out what their orbits are, we can figure out their sizes, and hence we can figure out things like their composition and their surface temperatures and really kind of try and visualize them, and this is actually an artist from the Bay Area. So we now know that there are planets everywhere. Essentially, if you were to go out and look up at the night sky tonight and pick 100 stars, essentially all of those would have planets going around them, and about 20 of those 100 stars would have a small rocky planet like the Earth in what we call the habitable zone, which is the region where liquid water could exist on the surface. And this is something, again, I want to emphasize this, that has been enabled by the development of an instrument, by engineering this Kepler spacecraft with the ability to measure very precisely the brightness of stars and to watch as planets pass between us and the star and to watch for the little dips in brightness that occur as the planets go past. Some other engineering developments have really given rise to other revolutions in our understanding of our place in the universe, and one of them was this really pretty basic by today's standards telescope that Galileo didn't design but that he used to look up at the sky, and you see some scan of one of his notebooks there on the right as he watched the position of, didn't know what they were at the time, but these little points of light that were moving around Jupiter, and he realized that these were actually moons that were in orbit around Jupiter, and this was really revolutionary in our understanding. There's some experimental confirmation that the Earth is not the center of the universe, right? Instrumental engineering development that was used by a smart person to figure out really a paradigm shift in our understanding of our place in the world. And then in the early 20th century, Edwin Hubble used the 100-inch Hooker telescope down, shown in the center image here, and measured the distances to galaxies and combined those with information about how far away those galaxies, how fast those galaxies were moving, and was able to determine what we now know as Hubble's law, which is an indication that the universe itself is expanding. So again, an engineering development that led to a revolution in our understanding. Actually here, that a lot of people thought at the time that the galaxies that Hubble was looking at were actually within our own Milky Way galaxy. They thought they were clouds of gas, that they were nebulae that existed within our own Milky Way. And Hubble and the work of others who were working alongside him resulted in this, again, paradigm shift, this realization that the universe was way, way larger than we ever thought it was, and that our galaxy was actually one of many galaxies in the universe. And so, again, sort of thinking about engineering, thinking about how this can sort of result in changes in our understanding. So we've had, Galileo and Edwin Hubble and then Kepler and similar instruments like it in that order. Kepler showing us that planets like the Earth are common. And the point that I'm making here is, can we do an engineering development program that actually leads to the next scientific revolution, which I'm going to talk about, which is the detection of life elsewhere in the universe. Is life unusual? Is life unique here on Earth, or is the life elsewhere? And particularly now that we know that there are tens of billions of habitable planets in our galaxy, are any of those actually inhabited, or are we the only one? I think that seems unlikely to me, but we've got to go and do an experiment. Also was struck by the fact that we had this anniversary of the Apollo program this year, 1969, 50 years ago. Neil Armstrong looking back at the Earth from the moon, and there's this great quote where he stuck his thumb up and covered up the Earth, and basically everyone that everyone that's ever existed behind your thumb here, enabled by this. And I don't know who of you have been to any of the NASA centers, but particularly the Johnson Space Flight Center in Kennedy and the center in Huntsville, Marshall, where they actually did this amazing engineering challenge that enabled us to get this sort of paradigm shift, this change in perspective. Neil Armstrong, one of 24 people to leave low Earth orbit and to go around the moon and to look back and to have this vision. And it strikes me as well, sort of in the context of, is there anyone else out there, that for a brief period around the end of the 1960s and the beginning of the 1970s, when 12 humans walked on the surface of the moon, there were 2 inhabited planets, or 2 inhabited worlds, I guess, for a while, right? There was the Earth and there was the moon, and we knew, we became sort of, maybe not an interplanetary species, but we set foot on another world. And I think, I don't want to kind of underestimate or underemphasize like how amazing that was then, and how much more amazing would it be for us to find that actually life took hold independently somewhere else. And so that again is what the experiment that we're doing is about. Another amazing engineering result. This is actually a composite image, but it's basically a photograph. This isn't an artist's impression. This is an image that was stitched together from a number of observations by the Cassini spacecraft. So this is a spacecraft, I guess, sort of the size of, I think it's like the size of a large SUV or sort of a minibus kind of size, that the engineers sent out about 1 billion kilometers. It flew out past Saturn. It turned back and captured this image of Saturn, backlit, the sun here shining through the rings of Saturn, and then the reflections and shadow of the rings on the surface there. And aside from what this tells us about Saturn, and aside from the fact that, what it tells us about engineering and our ability to send things here thousands or tens of thousands of times further than the moon is. The moon's about 250,000 miles, and again, I'm switching units here, but the planets are hundreds of millions or billions of miles away, and the ability to go out there and take this picture again, sort of through an engineering achievement, I think is kind of amazing. But it's also amazing because this picture is also parallel to the one that I showed you with Armstrong looking back from the moon, because you're all in this picture. You're on that pale blue dot, as Carl Sagan said in reference to an earlier picture that's here between Saturn's rings. And so, to some extent, kind of traveling out and looking back tells us about ourselves, which I think is really kind of cool. And I think, again, sort of this search for life elsewhere is also something that's going to tell us about ourselves a lot as a species and as an inhabited world here. If you want to go to the nearest stars are 10,000 times further away than the planets, so that's really hard. So if you want to look for life elsewhere, one place that you could start is in our solar system, and this is an example of a detection experiment in the solar system. Obviously, this photograph was not taken on Mars. I think these two were. If this was on Mars, then I think we'd be done with the experiment so far. But this is in the Mars yard down at JPL, where they developed the Curiosity rover, and it's going around kind of scooping up dirt and sniffing dirt on Mars and trying to figure out, at least are the precursors to life, is there biochemistry, or there are sort of organic materials. It's not a life detection experiment in itself. I think a lot of people are arguing for this kind of thing to go on a future lander to Mars, which actually might be able to detect biology directly, so it's still kind of a little bit inconclusive. But again, the sort of in situ sampling, I'm going to tell you about really like 3 ways that we could look for life in the universe. And one is to go directly and actually kind of look for chemistry to kind of scoop stuff up and sniff it. You might want to fly through the plumes that are coming up from the subsurface oceans on the icy moons of Saturn and Jupiter and we've already proven that we can get out to Saturn, send a probe that flies through there and does some biochemical measurements. You might also want to go to the nearest stars, and I'm going to tell you a little bit about Breakthrough Listen. Has anybody seen this slide, or you know what this is, yeah?
Yeah, it's one of the experiments that Stephen Hawking proposed about sending little solar pulse in the universe with lasers that push those little sensors and little sheets.
Yep.
To the velocity of close to light, the velocity of light, at least
20%, yeah, that's right.
Something like that.
Yeah. Yeah, so I mean, this is the Breakthrough Starshot initiative. So this is the sister initiative to Breakthrough Listen that I'm going to tell you about. It's kind of nuts. I mean, as engineers, you should be looking at this and going, wait a second, you're going to take a gram-sized spacecraft, you're going to hook it up to a solar sail, you're going to build a laser array which requires, the power of a small city to run. You're going to accelerate this thing to 20% of the speed of light. It's got to get out to the nearest stars. It's going to run into a bunch of interstellar dust along the way, which is probably going to blow a bunch of holes in this thing. How is any of this going to work? And actually, nobody really knows if it's going to work at all. This is sort of, big engineering dream sort of stuff where people are trying to solve these challenges one by one in hopes that it one day may become possible. But I'm also kind of glad, that people are doing, again, these sort of, I'll say it, kind of outlandish experiments, these outlandish ideas that they're coming up with, because, someday we're going to make developments that maybe will lead up to this, or maybe there'll be kind of other developments that take place along the way that will enable us to expand our capabilities. But this really is, the only thing sort of is in as advanced a stage of design that really might have a chance of going to nearby stars in our own lifetime. And even this is going to be limited to a small handful of nearby stars. So in situ sampling really is only going to work in our own solar system, at least for the foreseeable future. So we have to do remote sensing if we want to look for life. And then there are a couple of things that you could look for if you want to do remote sensing. Again, highlighting some of the amazing engineering that's going on. So there's these kind of 30-meter class telescopes. Some of these are beset by sort of political issues that I'm not going to get into today, but there will be big telescopes that are constructed in various locations around the world, and there will be big space-based telescopes like the James Webb Space Telescope, or successors that have been proposed. One is called LUVOIR. There's a mission called HabEx, and the LUVOIR and HabEx and missions like it in particular that probably won't launch until the 2030s or even later are going to be our best shot at looking for signs of biology on planets going around other stars. Now, I already mentioned, planets are points of light at best in images. You saw that point of light that was the Earth as viewed from 1 billion kilometers away. Now imagine that you're looking at things that are trillions of kilometers away, and you're trying to sense those, and imagine the difficulty of doing that and the instrumentation that's required to do that. You probably will be able to do this for a handful of nearby stars, and what you would see if you were looking at planets around them for something like Venus or Mars, this is in the infrared, you would see absorption from carbon dioxide in the atmosphere and not very much else. If you were looking at a planet like Earth, then you would see signs of water vapor and ozone and other things that were a result of biochemistry. And it's very difficult to get a definitive result on this and to say, yes, that's water vapor that arose because of biochemistry rather than something else. It arose because there's a water cycle there, or things like methane and that kind of thing. But it can be an indication, particularly if some of these compounds are out of equilibrium, and it would actually require biology to sort of sustain that disequilibrium chemistry and enable them to persist over large periods of time. So that's a possibility, but again, it's really hard. So instead, maybe we could say, well, on Earth here, we have an example of biology that developed into intelligence, and intelligence that developed technology. And by analogy with biosignatures, maybe we can do remote sensing for technosignatures. And these will be powerful transmitters. They might be powerful lasers, like the Starshot laser, for example, that we talked about. They might be sort of perhaps a little bit more fancifully kind of megastructures that an advanced civilization might have built in orbit around a star. If you've heard of the term Dyson sphere or Dyson swarm, this is what we're getting at here, these kind of ideas that you might build huge energy collectors perhaps, and they'd be in orbit around the star. And maybe you could see signs, again, like those dips that the Kepler spacecraft sees as a planet passes between us and the star, that maybe if there's some artificial structure there, you might be able to detect dips as that is moving around. And again, you might say, well, Steve, this all sounds a little bit nuts. Why are they using radio? Why are they using lasers? Who knows what they're doing? Who knows if they're even out there, or if they're even building this kind of stuff? And those are valid criticisms. And we could just kind of decide at this stage, okay, never mind, we're not even going to try and look for them, or we can actually go out there and do an experiment. And that's what we're doing. So this experiment kind of has its heritage really from some experiments that were done by Frank Drake at the Green Bank Observatory in 1960. Here is Frank with the Taytal telescope that he used at the time. And Frank looked at two stars, and he used a single tunable radio channel. So he had a spectrometer on the back, and he basically kind of dialed through the frequencies and really listened for anything odd. He found kind of one or two odd things, which I think later turned out to be aircraft. And this was sort of the beginning of really what plagues us as scientists who are trying to look for technosignatures, is that our own technology really is far louder radio wavelengths than the things that we're trying to look at that are coming again from typically trillions of kilometers or further away. So even a cell phone or a satellite or a plane or whatever near the telescope is going to be deafening to the instrument if it's pointed in the right direction. Here's a little kind of fun thing that you can play around with. Has anyone here in the audience either seen or played around with one of these little devices? Really fun. I mean, you can see they're like $30 on Amazon. So this is software-defined radio, and you can download some free software. There's some videos online that'll help you install the software that goes along with this. And you can use these to pick up FM radio stations. You can use these to pick up plane transponders, which is kind of cool. So you can actually decode the ADS-B messages from plane transponders, and that's the plane telling you, this is my tail number, or my call sign, this is my location, this is my altitude, this is my speed and heading. And you can decode all of those little antenna that you hang out the window. Again, with this sort of $30 kit and some free software, you can pick up vehicle car key remotes. And there's some people that have done hacks with these where they're like intercepting somebody's car key and using them to do kind of things that are probably of questionable legality, but sort of fun to play around with. And some of this is like white hat hacking sort of stuff, where it's like, hey, Jeep, you have a vulnerability in your vehicle unlock system that we uncovered using this. But a lot of fun stuff. Software-defined radio, go check it out. And you can actually build, in the same way as probably like my grandfather would have ordered in a mail order catalog the pieces to build a hardware radio, a crystal oscillator and an amplifier and an antenna. You can do all of that in software now, and you can drag these little blocks around and kind of chain them together. And if you're thinking about going into RF engineering, this is a really great way to experiment with that. And there's actually a whole open source community, the GNU radio community. They have a convention every year, which is really fun. I mean, I've been along to this for a couple of years, and you meet kind of a bunch of really wild people that are using this for all sorts of applications: commercial, military, educational, scientific, and it's kind of neat. And this comes with a tiny little antenna, which again is not really going to cut it if you want to look for technosignatures that are coming from interstellar distances, so we're going to have to upgrade. This is what you would see actually with some software called GQRX, and this is an example of one band. I'm not going to really kind of go into details of what too much of what the plot is here, but this is a range of frequencies. This is just a screen grab from this that I actually just found on the internet, but this is what you'd see if you fired up the software. And so you see in the top graph here, intensity as a function of radio frequency. This is pretty low frequency here, but you could do this in the FM band, and you'd see a bunch of FM stations that are sticking up above the noise. And then you see below it here, so again, this is the same information, but frequency now as a function of time in the vertical axis, and the intensity of the signal is represented by the color scale here. And so there's a lot of things, as I mentioned, that are transmitting. You might see FM stations here. If you're in the FM band, you might see TV, you might see GPS satellites, you might see a whole bunch of stuff. But this image here, again, frequency on the horizontal axis, time scrolling down on the vertical axis, and then intensity as the color. This is called a waterfall plot because it's kind of like water going over a waterfall. The water that came over the top most recently is at the top, and then it's scrolling down, time scrolling down towards the bottom. If you're a Python programmer, there's tools that we have that enable you to read these in as an image. Basically, this is just an array. It's a value as a function of frequency and time here. And so you can then play around with these and do some data analysis, even run some image processing tools or signal processing tools on that in Python. And I'll give you some pointers as to where some of that software is a little bit later in this talk as well.
Guys, by the way, if you have questions, raise your hands.
Oh yeah, sorry, I have a tendency to kind of ramble. Yes?
So have you tried going into like longer wave radio waves?
So we have not gone longer wave, i.e. lower frequency than this, certainly. And part of the reason why is that actually the Earth's ionosphere is not transparent to radio waves below a few megahertz. So you're just going to get kind of bouncing our own stuff off the ionosphere. So you have to go from 10 or 20 megahertz and above. Typically, we're doing some kind of pilot programs now that are at sort of 60 or 80 megahertz up to about 300, but the majority of the stuff that we're doing is gigahertz and above, sort of 1 to 10 gigahertz typically frequencies. And there's not necessarily kind of that good of a reason to start there and to do that, other than that you have to start somewhere and that we have instrumentation that you can plug into. There's no real reason to believe that a techno signature might preferentially appear at those frequencies rather than some other frequency. Yeah.
Could you talk a little bit about how you filter out noise?
Yes.
Also, yeah.
I'm going to get to that in a little bit, so come back to me if I don't answer your question later in the talk. Okay. So I mentioned, already there are hundreds of billions of stars in our galaxy and probably tens of billions of habitable planets, and then there are hundreds of billions of galaxies in the observable universe. And again, one of the amazing engineering achievements of recent decades has been the Hubble Space Telescope, and this is just a section of the Hubble Ultra Deep Field. So this is one of Hubble's deepest images to date. This is basically several days of open shutter time where it just stared at one point on the sky in different filters, different wavelengths of light. The size of this entire image is about the size of a grain of sand held at arm's length. So this is a very small region of the sky. And there's a handful of stars in this image. There's a star there. You can tell it's a star because it has these diffraction spikes around it. There's a star up here. Again, you see with the diffraction spikes. There's a couple more that are kind of off the frame here. But the vast majority of things that you're seeing in this image here are galaxies. So that's a galaxy, a nice little spiral galaxy. This is also a spiral galaxy relatively nearby, another spiral here. But even these little red things and these faint blobs and little kind of distorted things going off into the distance, even stuff like that little thing there, these are all galaxies. There's about 10,000 galaxies in this image. The brightest star in this image, I think it's this one is the brightest in the field, is about 10,000 times too faint for your naked eye to see if you're looking at this region of sky. And so what you're seeing here is a region of sky the size of a grain of sand held at arm's length that would appear completely black if you were to just step outside and figure out where the Hubble was pointed at this time and look at it with your own eyes. And then the Hubble looks at it and it sees 10,000 galaxies going out to the edge of the universe in this little region of the sky, which is typical of any place you might choose to point the Hubble. I mean, some of it there'll be stuff in the way, some of it there might be our own Milky Way galaxy in the foreground. But wherever you were to point it, you see these galaxies, going off into the distance, and then you do a little bit of kind of back of the envelope math, and you realize that in the observable universe there are hundreds of billions of galaxies. So you've got hundreds of billions of stars in a galaxy, and you've got hundreds of billions of galaxies in the universe, and so maybe you've got something like 10 to the 22 places where life could arise. And now, if you were kind of doubtful about there being life elsewhere in the galaxy, I mean, you've got to really think it's long odds if there's no life anywhere else out there in the universe. Yeah.
Whenever I get interested in this and I start to watch some videos or read some books about the subject, I get really depressed. Because I feel that I'm really, really insignificant.
Yeah.
How do you deal with that?
Well, one thing is, yes, I agree. It's sort of this sense of like we're just living on this little speck kind of somewhere out in the remoteness of space. One thing that I find amazing, as a scientist and also kind of, again, pointing to these engineering achievements is that as a human species, we've actually developed the equipment that's enabled us to understand our place in the universe. I mean, and if we are the only minds in the universe, if there is no intelligence elsewhere, then in some ways we're kind of the pinnacle of what the universe has produced, right? We're the most complex, machine really that has arisen naturally, and then we ourselves are producing machines that are enabling us to have this incredible viewpoint. And one of the things that gets me as well, I mean, this is sort of a little bit off topic, but if you go out to, go up to the Sierra Nevada or somewhere where, there's a dark sky, you can actually see the Andromeda Galaxy with your naked eye. It's our nearest neighbor galaxy, about 2 million light years away. And it's about 4 times the size of the full moon on the sky. I mean, you think of these things as requiring really high magnification to make astronomical observations. They're really more likely to require just a lot of light gathering power, essentially a big lens or a big mirror, a big light bucket to collect all the photons. It's not like we're kind of going enhance, and kind of zooming in and getting more and more detail. Andromeda's really big. It's actually big enough that if you want to, take a map of it with a Hubble Space Telescope, as some of my colleagues over in astronomy have done, it takes a really long time. You have to kind of move this grain of sand size, pointing thing around and make, do hundreds of exposures basically to get that map. Again, this is sort of a little bit of a diversion, but those photons that are coming from the Andromeda Galaxy, that are hitting the back of your eye, have been traveling for 2 million years across interstellar space, and that's a relatively close galaxy. And I think that is kind of amazing. Somewhere like in sub-Saharan Africa, when humans were just beginning to come about, the light left that galaxy, and then all the intervening steps in human evolution happened, and we migrated and kind of ended up, settling everywhere in the world. And then we developed science, and we developed technology, and we developed engineering, and we built all of this stuff. And then here you are, or here the Hubble Space Telescope is, or whatever, 2 million years later, and that photon's like, boy, I'm tired, just flew in from the Andromeda Galaxy, and boy, the joke's not really going to work, but hits the telescope, and boom, like pops out of existence. And I kind of feel bad for the other photons that, came all that way and just sort of, landed in a parking lot, or, bounced off the roof of a building, or, hit the eye of a cat or something, which didn't really appreciate what it was seeing, right? It's just kind of a weird answer, I know, to your question, but I think we bring meaning to the universe by being able to comprehend it in some way, and I think that is really kind of a cool thing, the fact that we can sort of build stuff that enables us to kind of figure out, oh, I know what's going on here. So that's, for me at least, kind of maybe thinking, maybe that's not satisfying to see your hands go up again.
From what you're saying. So how do we know that there's not huge civilizations just outside of our view that exist, but we're just only getting the photons from 2 million years ago?
Yeah, sure. I mean, this is a bit of a complicated question. So, the Hubble Space Telescope can see some of these galaxies you're seeing as they were billions of years ago, which is also kind of nuts. But most of the stars that you see in the night sky, you're seeing as they were a few years ago, or maybe a few tens of years ago. And so actually, I'm telling you this, maybe spending a little bit too much time on background here, because I've got to run out of time if I don't move forward, but telling you this in some way to kind of set the stage for, okay, we're actually going to look around planets orbiting nearby stars and just see if we find any of these technosignatures coming from there, in part because the inverse square law, the fact that you put a transmitter twice as far away and the signal that you receive goes down by a factor of 4, means that it's energetically a lot more favorable to look for things that are nearby. I'm going to move on. I can do kind of pop your hand up if you have questions, but I want to get through. Okay. Okay. So having said all that, where is everybody, right? This is a photograph of Enrico Fermi. Some of you probably heard of the Fermi Paradox, this idea that, if there's all this real estate out there where they could be living, why haven't we picked anything up yet? Why haven't we seen any visitors? Why is the best evidence of, extraterrestrials some shaky cell phone video that some drunk walking back from a pub shot, in a field in Ohio or something, I forget who it was, but some people have said, where are the gear shifters, from extraterrestrial spacecraft? If they crashed on Earth, shouldn't somebody be able to show us an example of this engineering that was not possible by human hands? Why haven't they landed on the White House lawn? Or why are they not kind of at least sort of there's no artifacts, there's no evidence that they're in the solar system. I mean, and a lot of this stuff gets pretty fringe, and I should say I want to stay away from kind of UFOlogy here, and definitely not about that. But nevertheless, we could ask this question, well, why have we seen no signs of them even in these experiments, SETI experiments? I think I've not actually used the word SETI before, but the search for extraterrestrial intelligence, the search for technosignatures, why have we not come up with anything yet? And I think I'll kind of cheat and tell you the answer. It's that we actually haven't really looked hard enough, and also that maybe we haven't had the technology beforehand to do a proper search. And again, I want to point back to some of the other technological revolutions that I illustrated, right? Those galaxies that Hubble was looking at were there all along, and they were receding from each other all along, and the information that the universe was expanding was there all along. But it took 100-inch class telescopes that only came around at the beginning of the 20th century. It took that engineering development to actually enable humans to get the data that they needed to show that was the case. And so we may be at the stage, we may not be, but we may be just at the stage where we have this kind of these developments that are taking place, which I am going to get to telling you about on the engineering front, that may lead to the possibility of a detection. And I'm not the PI of this project. I was just kind of sent out, I guess, because we had a lot of media requests when Breakthrough Listen was launched in 2015, and my boss said, can you do Fox Business? And I was like, yeah, sure. So here I am, in their studio in San Francisco, and I didn't see at the time, the host that was interviewing me, I didn't see all of the crazy graphics that they had, that somebody had just Googled, space videos, and so they had, pictures of, astronauts on the space station. They had, the Mars rovers driving around. I guess it's a bit more relevant since I had those in my talk. Just, space stuff, and she's like, what would aliens look like? I'm like, I don't know. But I think the reason why Fox Business were interested was because Yuri Milner, who is an internet billionaire, pledged $100 million through the Breakthrough Prize Foundation, of which he is also a co-sponsor, over 10 years to expand our capabilities to look for intelligent life beyond Earth. And that is the Breakthrough Listen initiative, launched in July of 2015 at the Royal Society in London by Stephen Hawking, who also was present at the launch of the Breakthrough Starshot initiative, which is one of the sister initiatives. And it's headquartered, the science team is over in the astronomy department here at UC Berkeley. So my boss, Andrew Simeon, is the principal investigator, and there's about a dozen scientists and engineers who are working on the team here at Berkeley to implement this project. So we have a slightly bigger telescope than the one that Frank Drake used. It's also at the Green Bank Observatory in Green Bank, West Virginia. This is the 100-meter Green Bank telescope. So the collecting area here is the size of 2 football fields. There's about 6,000 tons of moving parts on this. This is our chief engineer, Dave McMahon. He's actually in South Africa at the moment. But if you want to talk about the engineering aspects, come find Dave over in the lab and chat with him. You see for scale here, there are some painters who have just rappelled down from painting the surface of the dish, which they do each summer. They have some downtime where they're kind of in the structure here, giving it a new coat of paint. And some trucks for scale here. This thing rotates, the whole thing rotates on some railroad trestles down at the bottom here. And then there's also a huge bearing here that rotates so the thing can tip up and down. It's the largest steerable radio telescope in the world, and it's also, you hear it variously described as the largest movable structure on land, or the second largest movable structure, because technically the largest one is the sarcophagus that they rolled in over the remains of the Chernobyl nuclear reactor, but that just stays in one place after it's been rolled in. This thing we're using for 20% of the time that it's available, basically, so pretty much every day we're on the telescope taking observations for the Breakthrough Listen project, and so it's certainly the largest steerable object that I can control from my laptop, which is also kind of fun to do. This is the Parkes telescope in Australia. We also have about 20% of the time on Parkes and a similar instrument down there, and so we kind of cover the whole sky with these big single dishes. This is the largest steerable radio telescope in the southern hemisphere. May be familiar if you've seen, there's a movie, The Dish, which is really cool, about the moon landings and about how plucky engineers at the Parkes telescope saved the day for NASA by sort of filling in when NASA's stuff broke down to get those iconic TV images of Neil Armstrong on the moon back. It's kind of a fun watch. And what we do, and there's some links to the papers here. I can share slides with Nima or whatever if anybody wants to follow up on looking at some of these references. But rather than having that $30 little dongle that we have on Amazon that can tune to a couple of megahertz at a time, we spent a couple of $100,000 on high-performance computing hardware, and this is half of the cluster that we have at Green Bank right now. So these are a bunch of what we call compute nodes, each of which has, well, I guess in total here we have about 8 petabytes of storage on this system. And each of these nodes is writing 750 megabytes per second to disk that's coming from the telescope. And essentially what we're doing, again, sort of 20% of the time, hundreds of terabytes a day of raw data. We're tuning to billions of radio channels at a time, and we're doing this for hundreds or thousands of stars. So the experiment has kind of scaled up from Frank's 2 stars and 1 radio channel, not to dismiss, you know, the impact of what Frank did in 1960, but basically Moore's law has enabled us to scale this thing up and to build an instrument that really is, you know, pretty impressive. This is the most capable digital spectrometer that's deployed at any telescope anywhere in the world. Yeah. Because other people want to use the biggest radio telescope, or the biggest steerable radio telescope in the world too. And actually we purchased time, the Breakthrough Listening Initiatives have purchased time on Green Bank and Parkes. I probably won't get to this, but we have other instruments that we're deploying elsewhere where we can kind of piggyback on other people's observations, where we haven't needed to actually buy dedicated time to point the telescope. We just say, oh, you're looking over here, you know, I'm going to get a copy of the data and look for interesting signals while you're doing that. But trust me, I mean, 20% of the time is generating plenty of data. And, you know, if any of you are doing kind of, you know, math in your head, then you realize these disks fill up pretty quick. And so we actually only archive about 1% of the data. We do a reduction in size that really is just averaging in frequency and or time. And I don't want to kind of get into that in detail, but we can talk about that offline as well. Yeah. Go ahead.
Yeah, you say 750 megabits per second per computer node. What is a computer node?
Yeah, that's one of these 64 computers here. I mean, you only see 32 plus a spare here, but there's another 32 in another room. And so they each get a little chunk of the spectrum. They're each sort of dealing with a couple of hundred megahertz, and then you stitch all of that together, which gives you the 12 gigahertz coverage, again, compared to something like 2 megahertz typically with those $30 things that you can buy online. But otherwise, it's just kind of a scaled up version of that. So I've alluded to this already, but part of the problem with this search is that we're pretty noisy as a species. You know, we have a lot of radio transmitters ourselves, and even in the National Radio Quiet Zone, which is a federally protected area, both for Green Bank and the NSA also has a listening station out there, kind of just over the hill from Green Bank. So there's restrictions on fixed transmitters out here close to the telescope. They go around. I don't know whether there's kind of legal weight to this, but they ask people, you know, please don't have Wi-Fi in your house, and, you know, please don't use a microwave oven and this kind of thing. And actually, there's also people who think that, you know, Wi-Fi and PG&E smart meters and all this kind of stuff is messing with their brains, who go and move to Green Bank, West Virginia to get away from, you know, the electrosensitives, they call them. There's kind of an interesting New York Times article about this. And it's nice to have them there as well, because, you know, they complain vociferously if anybody, you know, is polluting the radio spectrum. And so they're kind of good people to have, you know, calling your member of Congress or whatever to say, you know, please don't allow this. But even there, you know, we do pick up in the data, you know, things like cell phones. There's also a famous story at the Parkes telescope of somebody thought that they'd made a detection of this fast radio burst. I'll talk briefly about FRBs as well, but they thought they'd found one of these that later turned out to be an impatient person pressing the button to open the microwave door before their dinner was ready, and a little pulse of microwaves came out and was picked up by the telescope, and they thought it was coming from space. So that's a fun story. So in answer to your question, you know, how do we kind of see through this noise? Well, the sort of analog that I have here is with a directional microphone, where, and thank you for all being very attentive and for not kind of you know, talking during the lecture here, but if you were in a noisy room where a lot of people were talking and you were trying to isolate one conversation that was taking place, you might want to have a directional microphone that you kind of scanned around the room, and you'd pick up a lot of background noise and a lot of other signals, but at some point, okay, I think that's a signal that I'm interested in. I'm pointing at that one person that I think is talking right now, and I'm picking up the background noise, but I'm also picking up this one conversation that I think is interesting, and then I move my directional microphone away, and I'm still getting background noise. Maybe the background noise has changed a little bit, but that one signal that I think is the interesting one has gone, and then I move my microphone back. Okay, I'm picking that signal up again, and I can do these on-off comparison observations basically with the microphone that can then help me localize the position of the one signal that I'm interested in. And we just do the same thing with the Green Bank telescope, which happens to be, very directional, and it's a high gain antenna, and it's a big dish here that basically enables us to point the telescope in the direction of a target of interest, in the direction of a star that we're interested in. So this is, some of you may have seen these polar plots of antenna sensitivity, so it's most sensitive in the direction that it's pointed in, and then the sensitivity falls off a lot, but it does also have these side lobes and also a rear lobe here, and this is the one that caused problems with the microwave at Parkes, because the microwave oven was kind of somewhere down here, and so it still has some sensitivity, even kind of pointing backwards. You think you're looking over here, but somebody behind you is, microwaving their ready meal and causing problems for you. But this is basically what we do. And we get spectrograms just like the ones that I showed you, these waterfall plots. So this is a waterfall plot from Breakthrough Listen data. And this is the output of one of those compute nodes. So again, you're seeing it's 187.5 megahertz in frequency. And then you're seeing the time axis. I guess the time axis is, no, that's right. Okay, yeah, the time axis is going down this way. And then you're seeing intensity as a function of frequency and time. And there's these kind of vertical black lines that you see in here, which are actually an artifact of the filter bank that we're using. It's basically the way that we channelize the data. But you also see some signals in here, and you can see these kind of wiggly signals that are picked up over here. So this is a real radio signal that's coming in from somewhere that the telescope is picking up. Oh yeah.
How did you find out that it was someone opening their microwave early?
Yeah, I mean, that wasn't my experiment, I should say, but they really, they were seeing a bunch of these. So there's a whole kind of story about the discovery of fast radio bursts. They did later turn out, like some of them really are astrophysical, some of them are really coming from galaxies that are billions of light years away, and the reason why we know that was because we were able to localize them and to find, the position of this thing corresponds with this galaxy. Some of them repeat, so actually you can go back and see the same signal coming from the same galaxy over and over again. But for these kind of weird ones, and this was sort of in the early days of work on fast radio bursts when people didn't know, are they astrophysical or not? They were plotting when they occurred, and they found that a bunch of them occurred around lunchtime, and astrophysics doesn't know when lunchtime is. So, and then they were like, oh wait, it happens when we're pointing in this direction, and wait, what's in the opposite direction? Now the cafeteria. And so it was some really good sleuthing actually that kind of, and then everyone's disappointed because they're like, oh, maybe none of these are real, maybe it's all just the microwave oven. But then later it turns out, no, actually some of them really are, and there's very good evidence now, there are some of them that are astrophysical, which is kind of cool, yeah.
Interesting, because this is a frequency that a microwave oven would fall into.
Mm-hmm.
How do you identify what an alien sounds like? I guess what frequencies are you looking for? I think most common to the analogous to what you're looking for.
Yeah, so this sort of got back to an earlier question or an earlier point that I made really, which is that I don't think there's any specific reason to target the frequencies that we're targeting. We're just targeting ones that there are receivers available at the telescope that we can plug into with sufficiently wide bandwidth that we can digitize that data and stream it to disk without being overwhelmed by too much bandwidth. So it's sort of, there's some engineering considerations really which have led us to focus on the region that we're looking at. But in this example, we actually do have data at 2500 megahertz that goes to the next compute node in the rack. But if you only had this one compute node, if ET is transmitting at 2500 and you're not looking at that frequency, you're not going to see them. So, that's another possible answer to, where is everybody? Might just be you're looking in the wrong place. But we're looking very hard, as hard as we know how to do in the places that we're capable of looking right now. We may change that at some point going forward. Yeah.
So, are there any plans to put telescopes like this on the moon to use this?
Yeah, that's a good question. Not telescopes like the Green Bank telescope, because getting it's like 8,000 tons, including the sort of support structure, getting that onto the far side of the moon. You can do the math in your head as to how much getting, like, I think a kilogram to orbit is to Earth orbit, low Earth orbit is still like $1,000. So I don't know. Somebody do that math and tell me how much it would cost to put the Green Bank telescope on the far side of the moon. There are ideas of putting low frequency, simple dipole arrays on the far side of the moon. I think right now, if you had, I don't know, $1 trillion to spend. I mean, we have $100 million to spend, but if you had $1 trillion to spend, or whatever it would cost to do this engineering thing that you're proposing, the right way, I'd probably rather, put some LinkedIn ads up and like hire everyone away from Google and pay them all $1 million a year and have them, or Yahoo, and have them come fix our data analysis for us. So that would be easier. There was one question in the back first, then I'll come to you, Neil.
What about cosmic background stuff? Because that's also a similar frequency, right?
Yeah, so actually it turns out that's not that much of a contaminant for us. Natural astrophysical sources of radio waves, the narrowest frequency emissions are from astrophysical masers, which are kind of weird objects. Again, I don't really want to get into this, but they're typically at least a few hundred hertz in width, and so most SETI experiments confine themselves to looking for signals that are just a few hertz wide. Essentially, there's too much energy packed into a narrow range of frequencies for it to be produced by a natural process. So we can get rid of this kind of broader band background of astrophysics and focus in on things that are artificial. The other thing is, even for broadband human-generated signals, there may still be a sharp edge there, so you could have something that's a kilohertz wide, but it still kind of cuts off much more abruptly than a natural source would do. Yeah.
How would you communicate with something that's on the far side of the moon if it's not kind of...
It's not line of sight. I mean, you probably would have to have an orbiting relay station, and again, this sort of highlights another problem with doing this, that by the time you have the technology to build this, there's probably going to be astronauts on cell phones up there, and it'll have ruined the whole kind of radio quiet environment anyway. So, yeah, you need some kind of relay or, data storage, then an uplink when the thing passes, and then it downlinks to Earth when it comes around the other side, that kind of thing. Okay, so so going back. So, how do you know if this is ET? Well, you do what I suggested that you do with the microphone, and you do an off observation, and then you compare the two things. So this is off the star. There's this star with some catalog number, and now we pointed off the star. And if you want to see whether you've seen ET, then you do that a few times. And what we do with Breakthrough Listen is we do 3 pairs of on-off observations. So you go on, off, on, off, on, off, and again, this is just the output of one of these compute nodes, so 187.5 megahertz, 5 minutes of time in each of these slots, so this is 30 minutes of time on the sky, with a little bit of time in between when it takes, and it's only really 20 seconds that it takes to move this 6,000 tons by a short distance to point to an off observation, and then you slew the telescope back to the point that you were looking at, and then you move it off again. And this is the output again. These are these waterfall plots, these dynamic spectra that are stored by the Breakthrough Listen backend that we then look at after the fact. And I tell our undergrads working with us this, it's trivial. Right now, all you need to do if you want to find ET is just look for things that appear in the top row when we're pointed at the star that are not there when we appear in the bottom row when we're pointed away from the star. Turns out there are a lot of interfering signals, so part of the problem is just dealing with the fact that you do this experiment, and again, over the kind of range of frequencies that we're looking at, there might be tens or hundreds of millions of signals, depending on where you kind of set your threshold, your detection threshold. And some of the signals are complex. I mean, some of them, like, the human eye might be pretty good at saying, okay, I think that's a signal, I'm going to kind of draw a box around that and call that a signal, but unless you have some kind of smart algorithm that can figure out this is, a distinct thing from this, or that these lines here should be treated similarly, and that thing should be treated differently, or these squiggles are part of the same signal. It's hard actually to build image processing algorithms that can do that very well. But just by looking at this by eye, again, you can say, well, okay, I think this signal here is probably the same signal as that signal there, these 2 vertical lines that appear in this plot. And actually, now that I look at this carefully, I think these 2 lines here are probably also the same signal as that. And maybe I can see something a little bit faint in here. It's kind of coming and going. Then you're like, wait a minute, 2,400 megahertz. And then you go and look at the back of your Wi-Fi router, and you're like, 2.4 gigahertz. I knew that number was familiar. 2.4 gigahertz and 5 gigahertz are frequencies that are in common use for Wi-Fi, and this is probably somebody at the telescope with their damn cell phone, waving it around, saying, why can't I get a Wi-Fi signal out here in the middle of the National Radio Quiet Zone? And the telescope is exquisitely sensitive, and even if you're not where the telescope is pointed at the time, you're like the equivalent of that microwave oven, and the telescope's going to pick it up, and we're going to see it in the data. So this is what we have to get rid of. We have to detect all of these junk signals and then throw them out. Yeah.
Why did they choose the National Radio Quiet Zone to be so close to a major city?
Yeah, that's a good question. I mean, I think probably what happened first was that Green Bank was built out there, and Moore's law is kind of our friend in that it enables us to develop this technology, but it's also our enemy in some ways, in that there's more and more technology. I mean, Elon Musk just launched. He has plans to launch thousands of these Starlink satellites that are going to provide internet access all over the world, and that's going to be bad for radio astronomy. It's going to be bad for optical astronomy as well, because the things reflect light. It may have been good enough at the time, basically, to get 3.5 hours outside of Washington, D.C. But I think it's also probably that the observatory happened. I'm not familiar with the history, whether the observatory was there first and then they kind of drew a box around it and said, let's make this radio quiet. But it's pretty good. I mean, it's radio quieter. It's one of the more radio quiet places in the United States. So I don't want to say it's terrible, but as there's more and more stuff in orbit, it's becoming more and more of a challenge. And so we have to either go somewhere else, like the far side of the moon, or we have to solve this algorithmically. And this is kind of the point that I'm going to get to next, basically. Did you have another question, Nemo? No? Okay. So we have a couple of papers from 2017 and then more recently in 2019 and associated data releases where we've gone through and we've said, okay, now let's actually look. So these you're now seeing what we call cadences. So this is one of those on observations immediately followed by an off observation. And here's an on, and there's an off, and here's an on, and there's an off. And if you were paying attention to what I was saying in the previous slide, so rather than being just the top row having a signal in the bottom row not, in the way that we've laid these out here, what you should see is alternating signal, no signal, signal, no signal, signal, no signal, and that's your ET candidate, that's your technosignature candidate. It doesn't really rise to the level of a candidate, unless you've got more confirmation. But these are sort of the best things that we've seen so far, where you can see the signal is drifting. I'm not going to get into this, but I guess I can in kind of questions afterwards if you want, but this is sort of another filter that we use for things that appear to be moving relative to the telescope because they've got a Doppler drift, and that's consistent as you come through here. So potentially this thing could be coming from a planet going around the star that we're looking at, and then we move away and the signal goes away and we move back and it's back. There's various reasons why we think that there were like 11 of these that came out of our initial data set, and there's various reasons why we think it's not ET. Mostly actually that most of them are at the same frequency, and it happens to be a frequency where there's a lot of interference in the spectrum, and so even when you do these kind of careful cuts and you're sort of passing things through these thresholds and requiring that they survive all of these criteria, you're still going to get a few things that kind of slip through. What you would want to do, if you really do, and you're welcome to do this, if you believe that any of these are ET, we publish the coordinates and the times that we were looking at them, and you could go and look back at that star again and see if you see the same thing, and that would actually be pretty exciting. If you look back at that star and you see that same thing that you don't see anywhere else, then that's very exciting. The fact is that we see some of this stuff in other places, and it all looks pretty similar, so we think that it's human-generated interference in these particular cases. I can come back to this if there's questions on that, but these are sort of the greatest hits, and they're not that great, but it's the kind of thing that we're looking for. So I kind of alluded to this, but there's a lot of kind of search space that we have to look through, and you could choose to put your resources in expanding the rate and frequencies that you're looking at. You could choose to put your resources in getting finer spectral resolution. You could get finer time resolution. You could get more time coverage. You could get wider bandwidth. You could expand the area that you're looking at, the field of view of your telescope. You could get better spatial resolution. And this is a plot from Mike Garrett, who is the director of the Jodrell Bank Observatory in the UK. And I think, I agree with Mike on this. There's kind of a couple of things that he says that we should highlight. One is actually field of view. So we should be looking at large areas of the sky, as well as looking at these kind of intense sort of staring observations of individual stars. But really kind of one of the key things here is, would I actually recognize a signal in the data if it was there? Would I be able to detect it and say, this one looks different to the others? And looking for a needle in a haystack is always kind of a difficult challenge, particularly if you don't know if there is a needle in the haystack and you don't know what the needle looks like. It could be a sewing needle, it could be a knitting needle, it could be the Seattle Space Needle. You really don't know ahead of time. It's like, what might ET be doing? Well, maybe something similar to us, maybe something different. Anomaly detection is really something that we care about, and actually, we really want to build a generalized anomaly detector. Silicon Valley has figured out how to do this, how to find ET. You go to Google image search and you type ET in, and you get lots of pictures of ET, including my favorite down here is ET dressed as Mr. T. So that's really like, wow, what a great algorithm that is, that it can find that. And so, some of you will be familiar with how Silicon Valley does this, and actually our sponsor, Yuri Milner, who's an internet investor, among other things, said at the launch of the program he wanted to bring the Silicon Valley approach to the search for extraterrestrial intelligence, and we interpret that, we're like, what does that mean? Well, we interpret that as using some of these algorithms, using these kind of, like big data, using sort of scalable approaches that can be applied to the big data, that can find either things that look the same in this case. So it's like, okay, these are, again, if you're familiar with how this works, this is basically a neural network that's been trained on labeled data. So it finds text that's adjacent to these pictures, and it says, oh, well, when ET occurs in text, it often occurs next to a picture that looks like this. And so it's then able to recognize the same as it could recognize pictures of cats and dogs. And this is how we train infants. We don't give them a vocabulary book. We do when they're older, but initially you train them by pointing at cats and saying cat, and you point at dogs and you say dog, and you're providing labeled data for the neural network that later, figures out how to process this. Problem then being, if you've trained a child to distinguish cats and dogs and you show them a horse, they're like, okay, well, it's either a cat or a dog, because those are like the two things that exist. So, I've got to put this in one category or another. So this is sort of the limitations of a supervised learning approach. If you're doing this, you might want to develop approaches that are more about clustering, where it's like, okay, I don't know that this is a cat, but I'm going to put all the things that look similar together here, and then call that something which later turns out to be cat, and these other things that look similar that turns out to be dog, and then there's this other thing that I don't know what to do with over here that looks nothing like these other two things. Oh, that's a horse, right? So this is really what we want to do, I think, with some of the data that we're working with, is to do, to build an anomaly detector that tells us one of these things is not like the other stuff. I'm rapidly running out of time. These are some examples of those fast radio bursts that I mentioned. So again, you'll see a waterfall plot at the bottom here. It's been rotated, so the time axis is now horizontal and the frequency axis is vertical. Just a preference as to how these are plotted. And these are a bunch of these bursts that were found from one repeating fast radio burst, actually using our instrument, using the breakthrough lesson back end of the Green Bank telescope. And it found a bunch of these. I'm forgetting exactly how many. It's like 20 of these coming from the same position. And this is also one of the reasons why we know that these things are astrophysical, is that they only appear, in certain locations. And this one was pointed at this thing that we know is the host galaxy of this object. And so we have algorithms that can find these things. But we've also, there was a grad student in our group, and now, like, for inexplicable reasons, the frequency axis is now flipped, so you're seeing these things with curvature going the other way. The FRB, if it wasn't obvious, by the way, is this quadratic shape here, so it has this distinctive curvature, which, again, I'm not going to get into why that is. But Jerry, who was a grad student with our group, trained a neural network to find things that looked like the ones that you saw in the last slide, the kind of 20 of them, and this algorithm found another 70 of them that had been missed by the existing algorithm. So that's kind of cool. It shows you the stuff hiding in data here, that if you have a smart algorithm that knows how to pull that out, then you have a chance of finding it. So, again, Andrew, our principal investigator, is also on board with this idea of building a generalized anomaly detector, or a sort of serendipity machine. And I'm not also going to really get time to go into this, but these are examples. So here you just have an on and an off, and here's another on and an off. And this is also work by Jerry Zhang here that you can go and follow up on. And Jerry trained a convolutional LSTM. So this is basically something that has some knowledge of how things evolve in time series. And then you have a discriminator network, which basically is saying, is this coming from real data or not? So you can read the paper if you're interested. But basically, what you see on the left here is real data, and then what you see on the right here is a generator that has been given the first bit of data, the on, and then has to predict what the off might look like. And then again, it's been given the on and has to predict what the off might look like, given what it knows about the whole data set and about how the data evolve. And it's pretty good at doing this. It knows that should be followed by something like that. Oh, okay, well, that's cool. That should be followed by something like that. Yeah, that's great. This should be followed by that. Oh, wait, hold on. There's something missing there. And actually this on the left, again, is what you would expect to see if this was a real technosignature signal, right? The on has the signal, the off has the signal missing, and the algorithm here has learned that normally when we see this, it continues. And so this is an anomaly. This is something that you could kind of draw a circle around and say, I want to look at that more. It's not necessarily ET, but it's something that an algorithm like this could flag as being something that you want to take a bit of a deeper look at. This is actually a detection of extraterrestrial intelligence. It's not aliens, but it is extraterrestrial because this is the Voyager spacecraft. It's intelligence because we built it and sent it out to the outer solar system. But I think this is really pretty cool. So this is now about 20 billion kilometers from Earth. And this is with the Breakthrough Listening Instrument at Green Bank. So this is an observation now. Instead of seeing the waterfall plot, you're just seeing the integrated spectrum where it's added up. And you see the carrier here, and you see the data channels here. And we're getting this thing loud and clear from 20 billion kilometers away, even though the transmitter is 20 watts. So it's like the light in your refrigerator basically transmitting across 20 billion kilometers of distance. And you have a big antenna with a lot of gain, and you point it at it, you can pick the thing up. And so, I'm joking, it's not ET, but it is a very good proxy for, what we're hoping to see, again, from distances that are thousands or tens of thousands times further away, and so for things that are millions or hundreds of millions of times brighter. There's a Jupyter notebook that you can go and play around with some of these data, and you can actually kind of zoom in from the spectrum as a whole. So again, this is one of those compute nodes, and then, so we don't do this zoom thing, but you can imagine, zoom in, and then here's the thing that I just showed you, and then zoom in again to get the data and the carrier and the other data signal here, and it's kind of fun to play around with the data a little bit yourself. There, again, I'll give you the slides, but you can go and kind of play around with some of the data and some of the Python notebooks and that kind of thing, and help us try and find ET. I'm going to skip over this. That's about the optical search, which I kind of come back to. Well, I want to answer a few more questions as well if people want. Plus, like talking to people for an hour in the dark kind of probably ceases to get fun for everybody involved at some point. I mentioned we have a lot of raw data available. There's actually about a petabyte of data that was released earlier this year to the public, along with some analysis software and some accompanying papers that go along with that. And I wanted to close by just showing this picture. My wife and I live down in Oakland, and we have a dog that we love to take hiking up in the Oakland Hills. And this is, I think, up in Redwood Regional Park, a photograph that I took. Beautiful natural place to go out and hike there. And sometimes it's a little bit worrying. You're hiking up there and you see these signs. It's like mountain lions have been seen in this area. There's activity of mountain lions. Well, should I be concerned? Should I be worried about the dog running into a mountain lion? Well, I don't see any mountain lions in this picture, so I conclude mountain lions do not exist. That would be a little foolish. If just because you don't see something, you don't think it's there. I mean, there could be one, hiding behind this log. I don't think there is, but there could be one, behind this tree. They might not be active at this particular time. I don't know much about mountain lions. Maybe they come out in the evening and we're there in the morning, or maybe they're actually kind of avoiding us for some reason. I mean, there's a bunch of reasons why we might not have made a detection that don't rule out the fact that they're there. It just means we haven't looked hard enough yet. And so, I think we shouldn't be discouraged that we haven't found any signals yet. And again, I'd just like to kind of point out that the developments in engineering really are the things that give me the most hope that we might actually be able to make a detection in the near future. And I want to close with a quote from another seminal paper, the 60th anniversary of which has just passed, by Cocconi and Morrison, two physicists shown here. And in regards to these technosignature searches, they say the probability of success is difficult to estimate, But if we never search, the chance of success is 0. And people might ask me, well, what are the chances of success for SETI today? And my answer is, well, they're better than they were in 2014 before the Breakthrough Listening Initiative launched in 2015. I can't tell you what they are, but I do know that we have more of a chance right now because of the incredible instrumentation and engineering and scientists that we have working on this, and algorithms and all of the stuff that we're learning from Silicon Valley and applying to this. We have more of a chance today than we really ever have done in human history, and that's kind of a cool position to be in and sort of a cool time to be working on this project. You can find us on the web, you can find us on social media, you can get my email from Nima, and I'm happy to take a few more questions. Thanks. And if you have to run out, I totally understand as well. I've gone over, so, yeah.
Yeah, thanks. First of all, thanks for being here today. That's fascinating.
Thanks.
Do we know what the fast radio bursts are? You mentioned they're
Oh, yeah. Good question. At one point, there were more theories as to what they are than there were actual fast radio bursts, which is not a good position to be in. It's been narrowed down a little bit. There is actually a very eminent astronomer, Professor Avi Loeb, who is the chair of the Harvard Astronomy Department, who has written papers suggesting that maybe they're aliens. I don't think they're aliens. I think aliens should be your last resort for an explanation rather than your first resort. I mean, I'm being a little bit disingenuous to Avi here. I don't think he's claiming they definitely are. I think it's been reported in the media sometimes that that's what he thinks. But it's like, well, what might it look like? Could it possibly be this? We're not. We think that we should rule everything else out first. What they probably are is something related to neutron stars. So neutron stars are the endpoint in the life of stars that are more massive than the sun. So they're bigger than things that will form a white dwarf, but they're smaller than things that will form a stellar mass black hole. They're still pretty extreme objects. So a neutron star is essentially the mass of the sun compressed to something that's about the size of the Bay Area. They're like 10 kilometers across. Some of them are rapidly spinning, so you may have heard about pulsars. Pulsars also just celebrated an anniversary, I think the 60th anniversary of their discovery by Jocelyn Bell Burnell using a telescope. Again, kind of cool engineering in the UK. Pulsars put out these bright radio pulses because they're rotating. They have magnetic fields, and they have kind of stuff that is electrons that are entangled in magnetic fields, and they sweep past you like a lighthouse and send out these pulses. Some of them are spinning as fast as a kitchen blender, which is also kind of nuts. So they're putting out, some of them are putting out one pulse every millisecond or so. They're rotating, once a millisecond. So something the mass of the sun, the size of the Bay Area, rotating once a millisecond. Some of them are so highly magnetized that if you put one at the distance of the moon, it would wipe everybody's credit cards on Earth. So these are pretty extreme objects, and they're sort of one of the most extreme objects that's known in physics. And so when you ask somebody, well, what could produce a millisecond long pulse that's coming from a distance of a billion light years away that we're still able to pick up, that is kind of pretty broadband in frequency. Kind of a natural explanation is some process coming from one of these highly magnetized neutron stars or magnetars. And so there's theorists that are putting a lot of thought into this, but I think it may be like a magnetar. Some of them may be magnetars being born, or some of them may be, the endpoint of the life of, a massive star, or a collision between neutron stars or something like that. But because we know some of them repeat, we know that at least some of them are not catastrophic events. They must just be something where the same thing is kind of, glitching in some way and putting out these pulses. So it's an open question, but I'd be willing to not put a lot of money, but I'd probably put a little bit of money on this being magnetars or something like that down the line. Yes.
There's a problem with doing infrared, like you do on galaxies to determine how far away they are, that the planets nearby just aren't bright enough?
Well, it's yes, in part. It's also a contrast issue, and in fact, we do have direct imaging of some planets, and I believe most of those are in the infrared, where there is more of a contrast between the planet and the star. So it's a little bit like a firefly next to a searchlight, right? It's not even necessarily just the brightness of the firefly, it's that you've got a contrast issue, kind of picking that out of the glare. And you can do that with an algorithm, or you can actually do that with some hardware, and actually there's experiments that have been done, and also experiments that may fly in Earth orbit, where you actually kind of maneuver a star shield into position at some large distance away from your telescope and position that really precisely so you block out the light of the star, and then you can just about see the light of the planet. Sorry, maybe I'm getting off topic, but finish it.
Can you also like just filter out the hydrogen and helium signatures or something like that?
Well, there's a lot of continuum light from the star as well, right? The sun puts out white light. Basically, it's not just putting out lines in hydrogen and helium. So you know, the sun is very bright. Seeing faint things next to the sun is very hard. So, you know, again, like, it's an engineering challenge. Basically, there's nothing in the laws of physics that tells you can't do that, but it's really pushing the limits of the instrumentation that we have right now. Yeah.
So, say you do find a signal, and how do you determine where it's coming from? Like, do you have to consider gravitational lensing?
Yeah.
Is there a specific procedure that you guys use for that?
That's a good question. I mean, I think gravitational lensing is going to be minimal for anything that's coming from a nearby star, and so the majority of the stuff that I've talked about today has been observations of stars that are a few light years away from Earth, where you know, you would expect it just to come in a straight line towards you, and for this on-off comparison to be sufficient. Now, you know, we've never got to this stage, but this is sort of the next stage we will get at, where we're excited enough about a signal that we've seen. We're like, we really think this, you know, looks very interesting. We got to call up somebody else at another telescope and have them take a look at this, and then they take a look, different conditions, you know, different time of night or whatever, different location on the Earth, point their telescope at the star, and if they see something interesting, oh, okay, well now, you know, now everybody's interested. Now we got to kind of marshal our resources, and we're all going to point at this. And I think what you would see, you know, if it really is a narrowband transmitter on a planet that's orbiting the star, you would actually see that shift, that Doppler shift, as the planet's orbiting the star, and it would correspond to the orbital period. And I mean, this assumes, you know, by the way, and I haven't got into any of this, but this assumes that it's a beacon that is switched on all the time. It's not something that goes on and off. You know, it's not something that's pointed in a particular direction maybe and then kind of scans across and points at somebody else. I mean, there's a whole bunch of, you know, things that I've swept under the rug today that, believe me, we've thought about and sort of worried about it at some level, you know, that are not the simplest case of either somebody with a very powerful transmitter that's transmitting in all directions all the time, or somebody that knows where we are and has decided to send a message our way and is kind of tracking us and beaming that message in our direction. So, you know, there are a whole bunch of circumstances where we might not see a persistent signal that don't necessarily rule it out as being real. But again, to paraphrase, you know, Cacconi and Morrison and some of these other people, well, and to quote directly Jill Tarter, who is one of the SETI pioneers over at the SETI Institute. So there's other work that's going on across the Bay and Mountain View at the SETI Institute. And Jill says, I like this quote, she says, "We reserve the right to get smarter." So, you know, maybe we're doing a stupid thing right now, or maybe you're like, come on, Steve, like, you really should be doing, you know, X, Y, Z. You shouldn't be looking at narrowband signals. You should be looking at broadband signals. You should be looking for intermittent signals. You shouldn't be looking for beacons. You should be looking for, you know, and whatever. You shouldn't be looking in radio. You should be using gravitons or something. I mean, whatever it is. Okay, like, we'll get to that once we've done the best experiment that we know how to do right now with the conditions and the instrumentation that we have available to us. And maybe that's sufficient. And maybe they are all over the place out there. Maybe there's tons of them. And, you know, the thing that blows my mind, as well as if you think about the discovery of extrasolar planets, I mean, I started the talk by saying we knew of 0, right? And then the first candidate planets that were discovered, people looked at the data and they're like, yeah, that's a bit weird, particularly since the first one that was discovered was actually in orbit around a pulsar. Like, planets around a pulsar, like, it's not where they're supposed to be. They're supposed to be around nice stars like the sun, and, you know, like, this is probably wrong. Turned out actually that was right. And then we found more, and then we found kind of giant planets like Jupiter, but they were in orbits like Mercury. So these were these hot Jupiters that were going on, like, should they exist? I don't know, those look weird. And then we finally, you know, we've just begun to discover rocky planets like the Earth, some of which are in kind of close to Earth-like orbits. And this is, you know, really 30 years on from the first detection of exoplanets, and, you know, several more decades from the beginning of this as a field of study. And so I think probably, you know, SETI is going to go the same way. If we make a detection, the first thing is going to be, really? Like, it's a bit weird. that's not very convincing. And then somebody else looks at it, it's still there. It looks like it's coming. Yeah, but seriously, like aliens? I don't know. Like, can we get any information out of this? No, it's really faint. It's just above the threshold of detection. We can't figure out what they're saying or if there's any encoding in this. Well, and eventually, you rule a bunch of stuff out, and well, okay, we think we made a detection. And then the really exciting thing is going to be detection number 2, detection number 3, detection number 100, detection number 1,000, and that blows my mind that I work on this every day, that we might get to the stage where we're in a similar situation to where we are with planets now, where, I don't know, any of you remember the last planet that was discovered? Do you remember a news article coming out about that? Was it splashed all over the front page of the New York Times or the evening news? It was probably buried somewhere. If it was even in there, it was in the science section somewhere, and you probably didn't hear about it. And it's kind of weird to imagine that we might get to the same stage with finding other civilizations. I think that the one sort of caveat to this is that if we can get a signal that we can decode, if we get a signal that we can interpret, and if it's, and the term that's used is anti-cryptographic, in other words, it's sort of one that basically contains the information that you need in itself to make sense of itself, so you can kind of unpack it and read it. And if it's like the blueprints for a star drive, or the secret to world peace, or immortality, or whatever, or if it's some super weapon that destroys us all, or whatever. I mean, there's a number of kind of sci-fi scenarios that you could come up with here. I mean, that's when kind of all bets are off in terms of sort of once we begin to understand signals and their information content, but we're not anywhere near there yet. We're just kind of trying to find the things, trying to really, it's sort of, I started off with, I think the first slide was, are we alone? And I guess you can't prove a negative, so we're never going to sort of be able to turn that around and say, yes, we are alone, there's nobody else out there. But I think if we make one other detection, a single detection, there's going to be more that follow. The only weirder thing than there being one inhabited planet in the universe would be if there are exactly 2.